On Canvas, I have on the home page of Canvas, you can now go right below where it has office hours. Should be a little picture of like a PowerPoint slide. I should show you that. Maybe while you're finishing your homework, I'll pull up Canvas just so you can see. Yeah, let's just show them. So here, this is this touchscreen?
No, so the controls.
That's all right. So there's the home page. There's the home page. And there's this screen, and right up there in that corner, click on that corner up there. See that? The left-hand corner. There you go. There's the 2 first lectures. And if you clicked on that, then it would open up that lecture. It's taking you out to YouTube. So this is a YouTube link that is embedded in Canvas. And so you click on that, and you can listen to some or all of the lecture if you missed one of the lectures, or if you want to go back to where I went over IUPAC naming. Thank you. You can do that. And then from now on, shortly after each lecture, usually when I get to it, but hopefully in a day or two, I'll get them up there. This one today, I'll try to get up there soon, so that if anybody wants to review any of it, they can. All right, properties of alkanes. They are hydrophobic. They are non-polar. Now, to understand non-polar, you have to understand polar. To understand polar, you need to take Chemistry 1305, which you did, right? Okay. So if you didn't understand it in Chemistry 1305, let's just mention it real quickly. Polar. Remember, water is a polar molecule. Why is it a polar molecule? It goes back to the electronegativities of the elements that make up the water molecule. Electronegativity, remember, this is all reminding you of something you've already learned. Electronegativity is the attraction an element has for electrons. It is a relative number. It's a construct. It's a scale that someone developed and said, okay, if we look at it, oxygen has a relatively high attraction for electrons. Oxygen's, relatively speaking, has a 2.1. Fluorine has the highest, 4.0. So it goes from 0 to 4.0, this electronegativity. So this is a fairly big difference, but the hydrogen-oxygen bond is a covalent bond. It's sharing electrons, but not very equally. This is the big brother cutting the piece of cake and getting the bigger piece. All right? That's why mom comes in and says, okay, big brother, you cut it, and little brother gets to take the first choice, So that kind of gives the big brother some incentive to make them pretty equal. But, all right, so we'll get back out of the family situation here, back to bonds. But this is a polar bond. So this end of the bond tends to be negative, and that end of the bond tends to be positive. It's a polar bond. Well, in contrast to that is hydrocarbons are non-polar. So let's take a look at butane. Butane, we have carbons bound to carbons. They have the same attraction for electrons. So there isn't unequal sharing of the electrons, there's equal sharing. So there's no polarity. There's an equal sharing of the electron, these two electrons between those two carbons. Likewise with those two carbons. So whenever you have carbon-carbon bonds, they are completely non-polar bonds. And then what happens when you throw in the hydrogen bonds? Well, this has an electronegativity of 2.5, and the hydrogen is still electronegativity 2.1. Are they different? Yes. But they're not as different as your water. That's a big difference, 1.4. This is just 0.4 difference. So relatively speaking, this is a relatively non-polar bond, a carbon-hydrogen bond. So the molecule as a whole ends up being non-polar. It is not only not polar or non-polar, it is not soluble in water. So they are non-polar, these are alkanes, and they are not soluble in water. Or a chemist would say they are insoluble in water. Does gas and water mix? Gasoline and water? No, they don't mix. This is why they don't mix. This is the why. The one is a non-polar molecule, water is a polar molecule, and they don't have an attraction for one another. Polar solvents like water dissolve polar substances like sodium chloride or ionic or polar substances. Non-polar substances will dissolve non-polar substances. So oil and gasoline do mix. You got oil, you get gasoline in your oil, it will thin out the oil. It won't just float in there, it will thin it out. Okay, so they are non-polar, hydrophobic. They're not water-loving. They're not hydrophilic or water-loving. They're hydrophobic. They are less dense than water, therefore they do float on top of water. Alkanes do. Not all organic compounds float on water. Carbon tetrachloride is a very dense molecule. It's not soluble in water, but it sinks to the bottom of water. It's got a big 4 chlorines on it. It's real heavy. So, but generally speaking, hydrocarbons, carbon-hydrogen compounds, are less dense than water, and they float on water. Okay, odorless. Lower melting and boiling points than other organic compounds. Just a general trend. Now, whenever I put a graph up like this, try to get your feet on the ground, your bearings. What is this trying to say? So look at the axes. What is represented here? Well, on the x-axis here we have alkanes. These are alkanes with certain number of carbons in them. So here's an alkane with 6 carbons. What alkane are we at right there? Hexane. Up to decane and going on up. And what we have on the y-axis is boiling points in centigrade, minus 200 degrees centigrade, minus 100. Here's the freezing point of water, 0 degrees centigrade. Here's about room temperature, 100, 200, 300 degrees centigrade. And what you're seeing, without trying to memorize any of these numbers, get familiar with the general trend. As the molecule gets bigger, what's happening to the boiling point? It's going up. So there's a direct relationship between the size of the molecule and its boiling point. Size increases, boiling point increases. What's happening here with the size? 1 carbon, this is methane. And like up here we have decane. What's happening is that the molecular weight is correlating with the number of carbons. You add another carbon, it's a heavier molecule. You add another carbon, it's a heavier molecule. It gets heavier. Because it gets heavier, it's harder to get it to go into the gaseous phase, to float around by itself up there. It takes more energy to bump it up into being a gas. So below here, so above here, they're heavier, so they're not boiling. They're liquids. They're liquids at room temperature. You got to raise the temperature to get this to vaporize. Decane. Can you boil decane? Yes, but you got to get up to about 150 degrees centigrade to boil it, well above the boiling point of water. Okay, so that's just kind of, that general trend will hold true with almost any class of compounds. The bigger they get, the higher their boiling points get. It's a general trend. Okay, now let's look at reactions. And we're going to look at complete combustion. So under combustion, we're going to look at complete combustion. And what's characteristic about complete combustion is that it produces carbon dioxide. Now let's take this molecule here. This is methane. And just a little practical background here. I was down at church on Thursday and a UPS truck pulled up. I'm walking in and I look at the UPS truck, and on the side of it, it said, powered by natural gas. All right? And then a few days later, Friday or Saturday, I was driving, so this is downtown San Antonio. A few days later, I passed a UPS truck on the highway, not on the 1604, but on a side road. And I wondered if they're all powered by natural gas, and I looked, and it didn't say that. It didn't say powered by natural gas. Now, it went right by me, so I might have missed it. But it didn't seem to say anything there. So I kind of wondered if UPS, for the UPS trucks that are running downtown, are actually powering them by natural gas. And if they're out of the downtown area, they're not being too concerned, but they probably haven't shifted their whole fleet over to natural gas. So they said, well, we'll run the ones that need gasoline, we'll run out there, and the ones that we have converted to methane will run in the city. Why do you think they might do that? Less pollution. That methane burns a little bit more cleanly. Yeah, so complete combustion is getting you to CO2. So methane plus oxygen that is coming out of the air produces carbon dioxide and water. And so out of the back of that UPS truck is just carbon dioxide and water coming out of the exhaust pipe. And San Antonio city, and particularly within the city area where there's a higher traffic volume, the EPA monitors our air quality, monitors it, and says, hey, drive down the pollutants in there because it is affecting people's health. Asthma, different things are being accentuated by the quality of the air, or in the lack of quality of the air. And so UPS, and I don't know, Via Trans is going this way, some taxis, whatever, they're saying, okay, we'll run these things on methane and make them burn cleaner. Now, while we're on practical matters, CPS Energy. You come out of downtown San Antonio and there was a big billboard there, and you could tell that it was by CPS Energy, and it had a little flame. Let's see if I can draw a flame. I can't. Something like that. And here's your stove top and a little flame. And I think all it said, I don't quote me, it said something like, blue is good. Blue is good. Or blue's better. Blue flame is better. What do you think they're telling you there? They're paying for this billboard. You're burning their gas, and they're trying to tell you something. I don't know, you don't have to tell me what color your flames are at home on your stove, but if you have a stove that burns natural gas, tonight you go home and turn it on and look at the flame. See if it's blue. What color will it be if it's not blue? Yellow. It'll have a little yellow or an orange tinge coming off at the top. What is that telling you? That is incomplete. That's some incomplete combustion. If there is enough oxygen getting to that natural gas, it'll be a nice blue flame. But if you keep, spilling over the bacon grease on top of your burners, and they're starting to get gunky, it's still getting the gas, but it can't get the air. It's starting to starve off the air around it, and it's orange. And what's so bad about that? That is incomplete combustion. There's what's on your stove. You're still getting oxygen, but you're producing some carbon monoxide. And there it is, right in your kitchen. If all your burners are burning with an orange flame, and you come home and you're cooking for 4 hours and you start feeling drowsy, you're getting a little bit of carbon monoxide as you're cooking. So you want a blue flame. It's nothing wrong with your gas. It's wrong with your burners. You need to clean those burners and get a nice blue flame. And if you can't get a nice blue flame, then call UCPS Energy and ask them, what do I do about this? Say, you might need a new stove. You might need us to come out and check or something. They paid for a billboard up there to tell you to get a blue flame. And that's what they're telling you. All right, so let's get back to complete combustion. You can see on the homework, it said write out the complete combustion of butane and balance the reaction. So let's do this methane. All right. So a balanced chemical reaction, first of all, you have to have the right formulas for the reactants and the products. That's methane. That is oxygen. It's a diatomic element. That's carbon dioxide, and that's water. A balanced chemical reaction will have the same number of every element on both sides of the equation. If you had me for 1305, then you know this. This is the choo-choo method of balancing these. And I write him, say choo-choo, we're going to balance the carbons, we're going to balance the hydrogens, and then we're going to worry about the oxygens last. Not going to just fiddle around. So is it balanced? How many hydrogens are over here? How many are over here? Not balanced. We know right away it's not balanced. It has more hydrogens over here than over here. So let's start. There's one carbon here. One CO2 produces one carbon. Brings one carbon out in the reactant, in the products. Yes, there are 4 hydrogens. There are only 2 hydrogens here. So I can't change this formula to H4O. I can't change the formula. Water is H2O. What can I change? Coefficient. Coefficient. So what a coefficient does it need? 2. 2 times 2 is 4. So now the carbon and the hydrogen are balanced. So now I come over here on the product side and I say if that methane is going to produce 1 carbon dioxide and 2 water molecules, how many oxygens are going to be represented in those molecules? How many oxygens are represented here? 2. How many oxygens are represented here? 2. 2 times 1. There's an understood 1 right there. Every water molecule has an oxygen in it. by putting the coefficient. That coefficient doesn't just apply to the hydrogens. It applies to the whole molecule. So 2 times 1 is 2. I got 4 oxygens. What do I need to do here?
2.
Put a 2. Is it balanced now? Yes. Okay? That's the way to do it. That is one way of doing it. Another way to do it is to just roam around aimlessly for 30 minutes and say, no, the carbons are out, the hydrogen, the oxygens are back out. And it's a dog chasing its tail. This is a dog that knows where the rabbit is and is heading for it. So you do this one. This is the complete combustion of propane. What will the complete combustion of propane produce? CO2 and water. When we burn these hydrocarbons completely, that's basically what we produce. It's carbon dioxide and water. Whether we're burning coal or hexane or octane or methane or propane. No, the CO2 doesn't have to come first, but I usually just do them that way. They just need to be on the right side of the equation. They are products. Propane and oxygen are reactants. This is not an equilibrium reaction. This reaction is actually proceeding to the right. If it was an equilibrium reaction, that would be beautiful. It would tell us that we could easily convert CO2 back into this, but we can't. We've released a ton of energy over here. And to get it back requires all that energy. So that's why we're releasing the CO2. We can't just produce propane out of it again. Not unless we invest a lot of money in the energy to do it. Okay. Someone want to tell me their coefficients?
I have 5 in front of the first O2. And then I have 3 in front of CO2. And then I have 4 in front of H2O.
Okay. And let's just do the math. We've got 3 carbons here. We've got 3 carbons there. We have 8 hydrogens here. 2 times 4 is 8 hydrogens there. 3 times 2 on the carbon dioxide gives me 6 oxygens, and 4 times 1 is 10. 5 times 2 is 10. It's balanced. All right? Okay, let's do one more. Any questions on that one? Okay, you will have questions on this next one. This next one's a trick one. Let's do hexane. Complete combustion. Okay, are you running into a little bit of a snag? No? Yes? Oh, yours are color-coded. Oh, wow. Looks good. Just have you do my lectures. Color-coded lectures.
Whole number?
Well, it should be.
Like the coefficient can't be like a decimal.
Yeah, but you're on the right track. That's okay. You got 9.5. Yeah, but we're going to bump that up. We're going to make that a whole number.
Just multiply the whole equation by 2, and it makes it a whole number.
Yeah, there you go. Okay, so when you go on into this, just the way I've been doing it, you end up with an odd number of oxygens, right? So if I put a 6 there, I put a 7 there, 7 times 2 is 14. Everything seems to be just going along fine. And then 6 times 2 is 12 oxygens in the CO2s. 7 times 1 is 7. Oh, 19 oxygens. But oxygens are like shoes. They come in pairs. And there's 19 oxygens. That 9 oxygens is 18 oxygens. 10 oxygens is 20 oxygens. And you can see we're right between 9 and 10. So 9.5 or 9.5. But we have a coefficient with a fraction. And we'd like them to be whole number coefficients. But if you were making pancakes and you didn't want 12 pancakes, you wanted 24, you would double everything in the recipe. Double everything. So if you multiply every one of these coefficients by 2, what that does to the 9.5 is it makes it a 19. 18, 2 halves is another 1, that's 19. That makes this coefficient 2, this coefficient 12, and this coefficient 14. So that's the approach if you ever end up with a fractional coefficient. It's always going to be a half. I mean, you're either going to need an even number of oxygens or an odd number of oxygens, and an odd number of oxygens is going to be a half of an oxygen molecule. And to get away from that, because you can't find half molecules of oxygen, we multiply it by 2. And so what it really ends up meaning is that 2 moles of this will react with 19 moles of oxygen to produce 12 moles of carbon dioxide and 14 moles of water. That's what the coefficients are telling you. What is the molar relationships in this chemical reaction? Okay, let's just do one. Let's just go to this one. Let's go to the methane. And say you do have an orange flame at home. You're getting a little bit of carbon monoxide. Homes today, the circulation systems in homes, they're actually set to bring in about 20% make-up air. So even though your house is kind of tight, it is turning the air over in your house a little bit all the time for reasons like this. Other things that are accumulating in your house, it's just bringing in fresh air. So you might not kill yourself with your stove at home, but it could be making you drowsy and not doing you the best good if you got a bunch of orange flames there. So here, if we balance this one the same way, we're going to find a different balancing point here. We only get 3 oxygens here, not 4. Before we got 4. So 1 mole of this reacted with 2 moles of oxygen. Now we're going to have 1 mole of this reacting with 1.5 moles of oxygen. It's not getting the 2 full moles of oxygen it needs to produce carbon dioxide. And so it is forming carbon monoxide. We're starving it for oxygen. So it will balance out a little bit differently. Now we would multiply all this by 2 to get rid of that. And would actually end up with 2 of these. Yeah, 3 O2s, 2 carbon monoxides, and 4 water molecules. Whereas before we had 1 methane reacted with 2 oxygens to produce 1 CO2 and 2 waters.
Did you have a case where you're making carbon dioxide and carbon monoxide?
Yeah, and your car, if you analyze the exhaust coming out of your car, the carburetor, they're trying to get it to carbon dioxide. The best carburation is a ratio that burns all the gasoline to carbon dioxide. You get more energy with complete combustion. So, but if you analyzed almost any automobile, you would find a lot of carbon dioxide coming out, a lot of water, and a little bit of carbon monoxide. Carbon dioxide will suffocate you. Carbon monoxide will poison. It's a poison. It binds to the red blood cells strongly, more strongly than oxygen. So it actually, it actually takes up the spot on the red blood cell that oxygen is supposed to, where the oxygen is supposed to reside. And so you do breathe, you're breathing oxygen, but your hemoglobin is already saturated with carbon monoxide. And it can't get the oxygen into the body. Carbon dioxide doesn't do that. It's just in your lungs, and it will suffocate you, but as soon as you breathe oxygen, you're fine again. You're fine, but not with carbon monoxide. Firefighters that are overcome, asphyxiated, they're giving them pure oxygen. They will take them to a hospital with a hyperbaric chamber that will pump the oxygen up to 2 or 3 atmospheres, and they're pumping the oxygen into that body to dislodge the carbon monoxide, to get it off the red blood cells. So the person that has had carbon monoxide poisoning needs pure oxygen and to overcome the strength with which that's binding the red blood cells. Okay, halogenation. There's a couple of them being shown here. Halogenation. We're talking about halogens reacting with alkanes. Remember, here's your halogens. Fluorine, chlorine, bromine, iodine. They are diatomic. So in their elemental form, fluorine is a F2 molecule. Chlorine, Cl2, bromine, and iodine. So when we write them in a chemical reaction, when we show something reacting with bromine, we write it as Br2. Or if it's chlorine, we write it as Cl2. Just like when it's reacting with oxygen, we write it O2 because oxygen is a diatomic element. So let's take a look at this one. This is ethane reacting with chlorine. So ethane and I'm going to shift over now. We use molecular formulas for combustion, but in most all reactions from now on, you're going to use a line formula or a structural formula. And if we react that with chlorine, let me show you what's happening here. Just to kind of depict what is going on. This is halogenation. That would be the general name of the reaction. More specifically, it is chlorination, because it is chlorine that's reacting with the molecule. Chlorine is the halogen that is reacting. Chlorination, so chlorination is an example of halogenation. So what happens is this chlorine takes that hydrogen's place, and this hydrogen actually is taking that chlorine's place. So we got that chlorine going on in the place where the hydrogen was, the hydrogen coming off. And so you get HCl over here, and you get a chlorine right there where that hydrogen was to begin with. We have substituted a chlorine for a hydrogen. So the type, not the name, but the type of reaction is substitution. Now, you haven't been introduced to any other types of reactions, but you will be in Chapter 11. We'll come in and look at some other reactions, and I'll say this is a different type of reaction. It's not substitution. And I'll explain what that is. But then you might know what I mean when we're talking about types. There can be a bunch of different substitution reactions where something is substituting for something else. So that's not the name of the reaction. It's just a class, a type that it falls into. So if I finish this off, if I were just writing out this reaction, I would write it like that. So there is the reaction written out. This is a diagram showing you a little bit about what is going on. How is that reaction proceeding? It's proceeding by substitution. Boink, boink. Okay? Okay, this is just showing, here's cyclohexane. They haven't written all the hydrogens. There's 2 hydrogens on every one of these carbons right here. They've written these 2 to show you that one of these hydrogens is going to come off, and one of these bromines is going to go on in its place. Substitute for it. Follow me? So you get this molecule, which would be bromocyclohexane. Bromocyclohexane. And you get HBr. And when you write these reactions, I want to see all the products, not just the organic compound, but also the HBr or the HCl or the HF, whatever acid comes off. Okay. So from there, what I would suggest you do is finish off the last 2 problems. What are they? Number 7 and 8? So finish 7 and 8, and then you can turn your paper in up here, and we'll kind of review Chapter 10 and write some more things on the board.
Will we be getting this back at some point?
Yeah, this homework, you can turn it in now. I'll probably try to grade it later today, early tomorrow morning, mid-morning tomorrow morning, put it up there. On Wednesday, I will hand it back. You'll be able to see what you missed, and you will have 10 or 15 minutes at the beginning of class on Wednesday to ask any questions you want to about alkanes. And then we will have the quiz. All done? All right. Okay, I'm going to put some names of molecules on the board, and you can come up here and draw them. whoever wants to volunteer to draw.
Because when is it supposed to be like when we write it out like that and then
Well, whenever they're just methyls, then combine them like that. Do that. So don't say 2-methyl, 3-methyl. You see, you're just repeating yourself. You can say 2,3 dash dimethyl. There should be a dash, not a comma. Okay?
So like this one, wait, is this one with the methyl and the ethyl?
No, there's all methyls. So 2, 2, 4.
This one would be
So you need a dash here too. 2,2,4 dash trimethyl pentyl. Right. Now this one, they are not methyls. One is a chloro, one is a methyl. So they need to be written out separately.
And then for this one, could we leave it like that, or do we still want to sprinkle it out? Because I was confused on how to draw this on the top without.
I prefer this as a structural formula. This is a mixture of hybrid and structural. Okay, I don't mind if you have the CH3 coming off you here, but I would put the H above it. Okay, and then do. And this is actually attached to that CH2, CH3, and there's an H down here. 2 H's, 2 H's.
You'll start off with and then you'll have your O2, and then you're going to produce by adding your changes.
On A, is it 8? You don't count the one in the parentheses? No, because that's like a branch. Okay, so it is at 2. Wait, so which way is it? The way that I was doing it? No, for this one, yeah, I just did it because I was like for here, so like the 3 comma methyl has to. Instead of comma, it's a dash. But like otherwise, I don't have to do like what you were doing. Yeah. But I could do the 2,3 dash dimethyl for B, right?
Down here, I would like to see the structure. Actually, show me the structure. Yeah.
But this one is just the...
Yeah, that could be the molecular. Just do one. Yeah, just do one. Let other people, whoever wants to come up and do some of these, feel free.
Wait, did I do it the right way? I mean, he wants you to write it out. What if he wants like this? So yeah, I'm saying. What if I put the CH2 on just the bottom? Yeah. Or I mean, you put it on the top. It doesn't matter as long as you attach it to that. Okay, just make that change order. Alright. I didn't want to do that. It's a lot more. Yeah. Wait for C on the bottom. How are we doing that one? No, it's in this one. Why do you write it that way? Why can't I just put a 2-2? Because the chloral is different. Like, what are you going to say? Dichloral, methyl, Oh, you're right. Wow.
2 terabytes is really 1 terabyte.
Are all right. then, okay, and then this last page, I think everything's right. I think this is the right way too. Oh yeah, and then how does it go? So I know. Okay, this bottom one I haven't done yet though for number 8. So you drew out the whole entire butane, right? See? Or wait. And then there's a brome, so.
Yeah. Right, so you want to simply,
Kind of doing based off the example. Which way did he want us to do it though? That way or this way? I don't know. It looks the same pretty much, just all together.
Is that thing was drawing that?